Students, this is Miss Green, and this is day 2 of rotations. Today we're going to look at a rotation, how we can create a rotation with 2 reflections, and we can calculate that angle of rotation. We're also going to apply some of the knowledge that we have about rotations to real-world situations. Let me do this. I'd like a bigger slide. There we go. For a little review, I'd like you to go ahead and figure out what the coordinates of the image are for a rotation of 180 around the origin, and GH is a line segment, and G is at 2, -9, H is at -1, 3. So if you remember, the first thing you'll need to do is figure out the rule and then apply that rule to each point. These points. Now, you might ask, what can I do to kind of verify that I did it correctly? What I would probably do is do a rough sketch over here of 2, -9 would be down here somewhere, so that would be G, and H would be -1, 3, maybe right about there. So that would be H. So the line segment would look something like this. Then you would do your new points. Let me do that in a different color. Well, maybe not. Yellow might not show up. Oops. Just having fun playing with all these. How about blue? So now we're going to do -2, 9. That would be up here. And that would be G prime. And then H prime would be 1, -3. About right there. That'd be H prime. And sometimes it's a little hard to tell, but you can imagine making a little rotation, so you're going counterclockwise, although with 180 it doesn't matter which way you go, right? Counterclockwise 180 or clockwise 180 does the same thing. You're drawing part of a circle, and it's a 180, half a circle. You'd be up there, so the G would move up there, and then the H, if you think about it, then the H would be coming around the other way, and it would go 180 degrees, and it would end up being there. So, probably did it right if you got something that looked like that. Now we're going to do 270. So, if you remember the rule for 270, it's similar to the rule for the 90. It's similar, and I always double check my rule sheet here because I've been known, I'm directionally challenged, and sometimes I get it backwards, so I always want to make sure I'm doing it right. So the rotation rule for 270 is the XY becomes Y -X. So whatever X is in the pre-image, in the actual image, the X gets negated, the opposite sign, and I put it in the Y coordinate. So -4 becomes a +4 and goes here. And you know what I do? Since I've got 3 points, I will go ahead and do all 3 points at the same time. So I'm doing the same thing each time. So I take the X and put it in the Y. The X here is 0, -0, 0, so it doesn't matter. 2 goes here, and then I make it negative. Then I take the Y value, and all I do is put it in the X coordinate position. So 7 becomes, and the 8 goes here, and the -1 goes here. I would also draw or put both of these on here just to get a good idea and see if it looks similar, because then I know I probably did it right. So 270. So let's do the first one in red again. And X is -4, 7. 4 to the left and 7 up. And these are on top of you. So this is So go ahead and do that. That would be your x. And then y is 0, 8. So that's right on the top there. That's my y. And these are the same ones we did last time, so it might look kind of familiar, the shape that you're making. 1, 2, and 1 down is the z. I put that through a z so it doesn't look like a 2 when you're writing it out. That's why I do that. Well, pretend. It's close. All right, then we'll go to the blue and do the blue. And this time we're going to do 7, 4 for our x. 7, 4. That's my x prime of my image. And then 8, 0 goes here. And that's my y prime. And then -1, -2 goes here. And that's my z prime. And again, I would probably connect those and kind of see what it would look like. I'm in trouble there. Okay. Well, if my drawing were a little more accurate, yes, I could see it's the same shape and the same size. Something you might notice. So x was in, this is, let's call this coordinate 1, 2, 3. That's quadrant. Sorry, I said coordinate. Quadrant 1, 2, 3, and 4. If x is in quadrant 2 and it's going 270 degrees, it has to end up in quadrant 1 because it's going around and around and around and around like this. Y, it's right on the axis here. So this would be 90 degrees. Down here would be 180. So it makes sense that it would be right here would be 270. And then Z starts here. So 90 degrees would be in this quadrant, 180 would be here, and 270 would here. And obviously 360, I'd be back where I started. This is something interesting that comes out of analyzing rotations a little bit. And the first time you look at it, it looks a little odd, like what in the world are they talking about? But once you've done it a few times, it makes more sense. And once you see it, and I've got another example that makes it a little clearer. So any rotation, any one at all, is actually a composition of reflections across two lines. So I'm reflecting twice across two lines, but the two lines have to intersect at the center of rotation. So if you look at this picture, I have my two lines right here. I'm taking A and reflecting it here, and then I'm taking, then it's A prime, and then taking A prime and reflecting it over here. And it doesn't matter how far apart these, doesn't matter about how far apart these lines are from each other, you know, the angle. They could be closer or they could be farther away. But what's true is that this one, if you rotate it, this angle right here is half the measure of this angle formed. So it's kind of interesting. You know, do we really have to need it? No, not that much. But it's kind of interesting to see some more things that are true about rotations. I could take this, I think it would probably help if you could actually take something and fold it along this line, and you could see, if you're reflecting it, it has to be the same distance, right? So pretend it's not quite 90 degrees. Okay. And then you'd do the same thing over here. You'd reflect it over that. And that would be, if that's 90 degrees, that's like a 90-degree reflection there. It'd be something that kind of interesting. You could make some triangles and you could actually prove this to be true. So it's kind of interesting. This one might be a better picture. If you look at the diagram over here, it's saying that this right here is the image of two reflections of this initial one over here. So the first reflection was along here, and the second reflection is along here. And so this ended up being 70 degrees from here to here. Now, the total rotation, so if I started C and went to this C, that total rotation is double whatever that angle is. So the total rotation is 140 degrees, and that's because of that theorem we just looked at. And sometimes that's a little hard to see, but it's true. You can see though, if I reflected this, if I could fold it along here and reflect it, I would see how the B's are mirror images of each other. Then I would fold it along here and reflect it again, and now the B's would be this would be on the left and this one's on the right, so it's another reflection. So I've reflected it twice, and I've got the same thing as if I just rotated it once, 140 degrees. If you remember that video that we showed yesterday, here's a snapshot of it. So here's a bicycle wheel, and it has 10 sections with the spokes. It makes 10 little pie pieces. And it's asking what the angle of each one of these little, assuming it's all even, let's say they're all even, what is this angle right here if there's 10 sections? All the way around it's 360 degrees. So I would divide 360 by 10 and I would get 36 degrees. So this little thing, all the way around, these are always 36 degrees everywhere. And this is useful when you're doing anything that rotates. There are a lot of things, if you guys, records, you probably, it's a little old school, but you might know what a record is. And rotations, merry-go-rounds, Ferris wheels, lots of things going around and around. So if I hand turn this wheel, nobody's on it, I'm hand turning the wheel 36 degrees at a time. So I turn it and then I stop it. How many times will I do that? Well, I have to do that to get the red section right back where it started. So the first time I do it, it would be here. The second time, this little piece would be here. The third time it would be here. 4, 5, 6, 7, 8, 9, and then it would take the 10th time to get it back there, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gets it right back. So that would be 10. This would be 36 degrees. Now, thinking about that, how many 36-degree turns would it take to make 180 degrees? Well, that's half of 360, so 5. There's some interesting things to think about. There are some more further investigations. There's a Desmos activity that gets you into a little more detail. So this is a fairly short lesson today. And there's some Math Excel practice problems too that kind of go along with this. All right, I hope you enjoyed the rotations.